We live in an unimaginably vast universe filled with trillions of galaxies, each containing hundreds of billions of stars. Space is so enormous that we will never know every galaxy, but thanks to telescopes like Hubble and James Webb, we have charted billions of them and have peered out to the most distant reaches of the cosmos. With this knowledge, we can undertake the ultimate journey, one that carries us through the entirety of space and time. We will travel beyond our galaxy, toward the farthest horizons, taking note of the most breathtaking and significant landmarks along the way. It is a journey toward the edge of the universe. To understand where we are going, we must first understand what the edge of the universe truly means. When people talk about space, they are usually referring to the observable universe, sometimes called the Hubble volume. This is a spherical region surrounding Earth that contains all galaxies and matter whose light has had enough time to reach us. Light moves at nearly 300,000 kilometers per second, which feels incredibly fast on human scales, but across cosmic distances it is painfully slow. Anything beyond the Milky Way incurs a heavy delay between when it emits light and when we finally see it. Objects appear younger as a result, which is why astronomers rely on light years as a measurement of distance. A galaxy 1 billion light-years away is seen as it was 1 billion years ago. In this sense, the edge of the universe is not simply a place, but a time barrier, limited by the universe's age of 13.8 billion years. Because of this, the observable universe contains only galaxies whose light has traveled less than 13.8 billion years to reach us. The more distant the object, the earlier in cosmic history we see it. A journey to the edge of the universe is also a journey back to the very beginning. It is often said that a telescope is a kind of time machine. If that is true, then the James Webb Space Telescope is a TARDIS, whose ultra-sensitive infrared eyes are pushing deeper into the cosmos than any other instrument in history, revealing the universe at every stage of its life. During these 13.8 billion years, the universe has been expanding. We see the evidence engraved in the wavelengths of light reaching us. As space expands, it stretches the wavelength of light, a phenomenon known as redshift. Light from distant galaxies becomes elongated, shifting toward the red part of the spectrum. Redshift, symbolized by the letter Z, provides astronomers with a perfect tool for measuring cosmic distances and tracking the expansion of space. Our journey starts on Earth, an unremarkable speck even compared to our solar system. The Sun is just one of at least 100 billion stars in the Milky Way, many with planetary systems of their own. Yet the true scale of the universe doesn't reveal itself until we leave our galaxy. The Milky Way is the second largest member of a small neighborhood called the Local Group, containing more than 30 galaxies and hundreds of satellite galaxies. The Local Group spans about 10 million light-years, though its four largest galaxies lie relatively close together and are slowly drifting toward each other. Their mutual gravity is strong enough to overcome the universe's expansion. Because of this, we do not see redshift within the Local Group. Beyond it lies the Local Volume, a wider region extending 30 million light-years from Earth. This region includes the Local Group and more than 500 other nearby galaxies arranged into their own small clusters. One notable neighbor is the Council of Giants, a ring of 12 massive galaxies surrounding the Local Group. Many of these giant galaxies host their own smaller groups, such as the Sculptor Group, led by the Sculptor Galaxy. This starburst galaxy is undergoing an intense period of star formation and is one of the most luminous objects in our local region. Farther away lies the iconic Sombrero Galaxy, with its bright central bulge and distinctive dust ring. Even though it is smaller than the Milky Way, its halo glows intensely, and it sits within the Virgo 2 cloud, a string of small galaxies leading toward the Virgo cluster. The Virgo cluster is one of the densest nearby concentrations of galaxies, containing more than 1,500 galaxies. Near its center sits the gargantuan Messier 87, a supergiant elliptical galaxy housing trillions of stars and more than 15,000 globular clusters. At its heart lies one of the most famous black holes in the universe, the first ever photographed by the Event Horizon Telescope in 2019. This black hole powers a massive jet of plasma that shoots thousands of light-years into space. All these galaxies, including our Local Group and the Virgo cluster, lie within an even larger structure known as the Virgo supercluster. But this supercluster is only one lobe of something much larger, a massive, interconnected network of galaxies called Laniakea. This structure contains more than 100,000 galaxies and stretches over 500 million light-years. The galaxies within Laniakea are not gravitationally bound, but they are subtly influenced by the combined gravitational pull of the entire network. For decades, astronomers noticed that galaxies across Laniakea seemed to drift toward a specific region of the sky known as the Great Attractor. But this area lies behind the Milky Way's dusty plain, making it difficult to observe. With the help of infrared and X-ray surveys, we now know that the Norma cluster, located 250 million light-years away, sits near the center of this gravitational basin. But the Norma cluster alone cannot account for the enormous pull experienced by galaxies. Far beyond Laniakea lie two even larger structures: the Shapley supercluster, more than 650 million light-years away, and the Vela supercluster, around 870 million light-years away. Their combined gravitational influences help explain the mysterious pull of the Great Attractor. As we move deeper into space, we encounter some of the largest structures ever discovered. 1 billion light-years from Earth lies the Sloan Great Wall, a massive arc of galaxies stretching 1.3 billion light-years across. It is not entirely clear whether it is a single structure or a combination of several aligned superclusters, but it was once considered the largest known structure in the universe. At distances beyond 1.5 billion light-years, we begin to see objects that reflect the universe's more turbulent youth. Long ago, galaxies frequently collided, fueling bursts of star formation and activating the supermassive black holes at their centers. These active galaxies shine brightly in many wavelengths. Among the most striking examples are radio galaxies, which shoot out high-energy jets from their cores, powered by infalling gas. Some of these jets stretch millions of light-years into space. One of the largest known radio galaxies, Alcyoneus, spans 16 million light-years. Quasars, however, are even more extreme. They are powered by supermassive black holes that devour gas at ferocious speeds. The gas in their accretion disks becomes so hot that it radiates energy more efficiently than stars, causing quasars to shine hundreds of thousands of times brighter than the Milky Way. One of the closest bright quasars is 3C273, located around 2.5 billion light-years away. But quasars become far more common at distances beyond 8 billion light-years. This was the era when smaller black holes actively consumed abundant gas, making them far more likely to ignite into quasars. At these depths, we find large quasar groups, apparent clusters of quasars spanning billions of light-years. The largest of these, the huge LQG, appears to stretch more than 4 billion light-years across, though it may be a chance alignment rather than a true physical structure. Even more astonishing is the Hercules Corona Borealis Great Wall, an enormous region containing an unusually high concentration of gamma-ray bursts. Gamma-ray bursts are the most powerful explosions in the universe, often produced when massive stars collapse or when neutron stars collide. This region spans an unbelievable 10 billion light-years, making it the largest apparent structure ever identified. At redshift values greater than 2, we enter an era known as cosmic high noon, when the universe reached its peak rate of star formation. Young galaxies at this time produced thousands of times more stars per year than the Milky Way does today. Many of them hosted brilliant quasars, often hidden behind thick shells of dust. NASA's WISE telescope detected more than 1,000 of these obscured objects, known as hot dogs, dust-obscured galaxies. Eventually, at distances beyond 12 billion light-years, the expansion of space becomes so significant that galaxies move away from us faster than the speed of light. This does not violate physics, because it is space itself expanding. But it makes the galaxies, light extremely faint and redshifted, nearly impossible to detect. Only advanced infrared telescopes like James Webb can glimpse these ancient galaxies. These are the galaxies that formed shortly after the cosmic dawn, some containing the universe's first stars. These earliest stars, known as population 3 stars, helped reionize the universe, stripping electrons from hydrogen and helium gas. This period, known as the Epoch of Reionization, ended around redshift 6. In the search for the earliest galaxies, astronomers have found a few extraordinary candidates. GNZ11, located at redshift 11, existed only 420 million years after the Big Bang. Even more distant is HD1, estimated at redshift 13.27, formed just 330 million years after the Big Bang. Another candidate, discovered by the James Webb Telescope, is Glass Z13. Though their light has traveled more than 13 billion years to reach us, these galaxies are now far farther away. Because of the universe's expansion, their present-day distance is estimated at more than 33 billion light-years. At around redshift 20, we reach the end of the cosmic dawn and enter the dark age of the universe. This was the time after the Big Bang but before the first stars formed, when no light existed anywhere in the universe. The darkness we see in deep space images is actually the light of this ancient era. Beyond this point, no optical photons have reached us, because they would have originated farther away than light could travel in 13.8 billion years. As time passes, more ancient light will drift into view, expanding our observable horizon, but even then, these objects will appear as dim red smudges, frozen in time by cosmic expansion. Beyond all this lies the oldest light in the universe, the cosmic microwave background, a faint afterglow from when the universe was only 379,000 years old. These photons were once visible light but have been stretched into microwaves by cosmic expansion. No matter where we point a radio antenna, we detect this ancient radiation, the universe's own baby picture. This afterglow marks the true limit of what we can observe. Earlier photons were absorbed by the primordial plasma and never reached us. The light we see today has been traveling for 13.8 billion years, but the space it crossed has expanded to 46.5 billion light-years. That is why the observable universe is about 93 billion light-years across, even though the universe is much younger. But this limit is not the actual edge of the universe, only the edge of what we can see. If we could travel far across the cosmos, our observable universe would shift with us, and the Milky Way would appear as a distant, red-shifted infant galaxy. Most scientists believe the universe extends far beyond the observable horizon, but how far and what lies out there remain some of the greatest open questions in cosmology. To answer them, we must step beyond the particle horizon and into the unobservable universe. An exploration reserved for the next chapter of our journey.